It's Aiden Roy, and this is my Lab 6 magnetic molasses lab report. So the purpose of this lab is to investigate magnetic induction and eddy currents by analyzing how a falling bar magnet interacts with an aluminum tube and comparing the observations to computational models. The results we found were that the experiment time was 1.25 seconds. The computational time was 0.973 seconds. So some fundamental physical principles we'll be using is the Biot-Savart law, which describes the magnetic field generated by a constant electric current. We'll also be using Faraday's law, which is when the magnetic flux or magnetic field changes with time, the electromotive force is produced, as well as Newton's second and third law, where force equals mass times acceleration, and for every action there's an equal and opposite reaction. This is our observed model. Some initial conditions are the bar magnet and the stopwatch that we used. Our system is the bar magnet and an aluminum tube, and our surroundings is everything else around. So some of the data and calculations that we found, the mass of the magnet was 0.02 kilograms. The mu of the magnet was 1.477. The tube had a length of 0.3 meters with a width of 0.0065 meters, an inner radius of 0.024 meters, and then an outer radius of 0.0305 meters. We ran 3 trials and found an average time of 1.253 seconds. These are some of my computational models on GlowScript for the initial conditions. If you'd like, you can take the time to go through them. These are some more of the original computational models, trying to outline my process of going through it and how I tackled it. These are the results of my computational model. You can see over time how it kind of drops as it moves through the tube. So some similarities and differences between the models. The experiment time was 1.25 seconds, whereas the computational time was 0.973 seconds. Some assumptions that we made is that the bar magnet acts as a magnetic dipole to apply the Biot-Savart law. We also assumed that there's negligible air resistance, as well as there are only forces involved are the magnet and gravity. So some possible sources of error that could have caused this difference in times was that the electronic/magnetic devices in the surroundings could have affected the forces, as well as friction against the sides of the tube is not fully considered in the calculations, as well as human error. The stopwatch starting and ending may be inconsistent as it's purely based off of human eye and reaction time. So for the discussion, some what ifs. The resistivity of the conductor were reduced close as possible to 0. How would the dynamics of the falling magnet change? Due to Ohm's law, the induced current in the aluminum tube would be much greater, which in turn would create a greater magnetic force on the magnet and could counteract with gravitational force, preventing it from falling. What if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The induced current in the aluminum tube would be less since the holes would disrupt the current and the magnet would fall through much quicker.